Yes, hello.
Hello. So, hello in the second day of this training. I hope you found the session last yesterday interesting, and that you are looking forward to the rest to see how you can solve this randomization problem. Before starting, just let me ask you, please, for your own benefit, it's important to attend the 4 days because, as you will see, we are, each day complete on the other one and answering the questions raised already in the day before. So to have a useful training and be able to apply this in your research, you should attend the 4 days, the 4 lectures. So just to make it clear. So let me share my screen. Can you see my screen?
Yes. Yes.
Okay, so as Dr. Chahir mentioned yesterday, what we are trying to do in today and the 2 days of next week, we'll try to see how we can solve the problem of non-randomization, which there was a question yesterday if this exogeneity is realistic or not, but especially in public policies or in a lot of programs that are applied as discussed yesterday, we will find this problem of randomization. If I will take the example of TAKافل program, which I will use it a lot in the lecture today. So TAKافل is a cash transfer applied by the Egyptian government to women, conditional on sending children to school and to follow health checkup for children and mothers. So usually women who are selected to benefit from this program, if I want to, for instance, measure the impact of this program on their empowerment, usually their characteristics or what makes them being selected in the program of TAKافل would also affect their empowerment. So there is this non-randomization or selection bias that we wanted to see if I want to measure the impact of TAKافل, which is the treatment or this program on women's empowerment, I need to find a way to overcome this problem of non-randomization. And propensity score matching is one of the methods. The first method we'll give it to you during this training to see how we can overcome this problem, trying to answer questions as what would have happened to this participant, to this woman, if they didn't participate in the program. So I want to know if women who participated in the program of TAKافل and get benefit of this cash transfer are more empowered with women who didn't participate or not. But to do this in like idealistic world, it will have to be randomized sample, which is not the case. So in order to answer this question and to calculate the average treatment effect and being sure to say that yes, this program empower women or say no, this program did not empower women, we need to use a method as a propensity score method that we'll use today to see how I can find the average treatment effect. So the main idea is as if I wanted to compare the same woman if she benefit from the program with her situation if she doesn't benefit from the program. So assume that I am getting this cash transfer. I want to know if now I am empowered or not. So I want to compare my situation if I did not receive the cash transfer, which is not the case. So what we try to do is that we wanted to compare between what we call treatment group or the group who benefit from this program, or if I'll talk about a training in the labor market, or even sometimes in medicine or health economics, we can, for instance, apply new medicine or new vaccine on the treatment group, and we wanted to compare their situation with what we call a counterfactual group, or a group who did not benefit from the program or from this vaccine or from this training. So we wanted to compare between these two groups to see if the group who benefit from TAKافل or from this training are more empowered or not compared to women who did not benefit from the group. But as we mentioned, the problem that the characteristics or the fact that it is not randomized, the characteristics of women who benefit from the treatment may be already affecting their empowerment. So usually they will be poor, they will be non-educated, they are not employed. So all these characteristics not only affect the fact that they are selected or chosen to be treated or to benefit from this program, but also affect the outcome we are interested in, which is the their empowerment. Okay, if I wanted to measure the impact of specific training program on labor force participation or on employment status, so the group of persons who benefit from this training, who I will call treatment group, their characteristics affect their selection in the program, but in the same time, it can affect their status in the labor market. So because of this non-randomization or non-experimental design, the treatment and control groups will have already different characteristics from the beginning. So those women who benefit from takaful are not the same women who will not benefit from takaful. Maybe women who did not benefit from takaful are better educated, they are younger, so they are already more empowered compared to those who benefit from takaful. So in this case, I cannot really compare between them. And this is called, selection bias. So we need to be able to create or form a group, a counterfactual group that has it has characteristics that looks like the treatment group, but they didn't benefit from the program. Imagine that I want to compare my situation. So I am benefiting from the program now, and I want to see what would happen if I didn't benefit from the program. But because I already benefit from it, I will try to find someone who has the same characteristics as me, had equal distribution of the non-treatment variables, of the other variables like my education, my age, my geographical location, all the characteristics I can control. And I will say, okay, Racha and this person Y have the same characteristics. Racha benefits from takaful. Y did not benefit from takaful. So let's compare the empowerment level between Racha and Y. If Racha is more empowered than Y, this means that because of takaful program, she is more empowered. But if Racha is less empowered than Y, assuming that Racha and Y are comparable and they have the same characteristics, so in this case, takaful did not really affect Racha's empowerment. So this is the main idea, that we wanted to replicate or create a counterfactual group that would allow me to compare a specific outcome. It can be women empowerment, labor outcome, income, nutritional status. For instance, I can check or measure the impact of takaful, this cash transfer, on the nutritional status of children of the women who benefit from this program. So whatever outcome I wanted to measure, to compare, to see if this program or this treatment has a positive or negative or non-significant effect on this outcome, I need to create this counterfactual group that looks like the treatment group and compare the outcome between both. So in this case, the PSM, the main idea is that I wanted to find or to see what are these characteristics that exist before the intervention, okay, before benefiting from the program or the training or the vaccine, whatever treatment we are trying to measure, to test, before this, and to see what's outcome. And of course, because in a lot of cases, if I will take the example of takaful when it was applied in 2015, we didn't have the characteristics, or there was no baseline survey before the treatment. So it's not like I can compare the status of this person's before the treatment and after the treatment. We will see next Tuesday that if we have panel data, or if we have the same data, the same characteristics of the persons over the years, I can compare their situation before and after the treatment. But in a lot of cases, we have only cross-section data. We have a survey covering a lot of individuals. Group of individuals are benefiting from specific program. And we want to measure the impact of this program on a specific outcome. So I don't have the characteristics of the individuals pre the intervention, or I don't have all the data about. So this is why the idea of the PSM, that we will try to find a counterfactual group that have similar characteristics to the individuals who are benefiting from the group, the participants to this treatment or to this training, and I will compare between them. Okay? So then we will compare treatment and control groups, and so we will match between them and we will compare between them, keeping in mind that here we are matching between them based only on observable characteristics. things that I can measure. So if I want to someone who looks like me, so I will check a person with characteristics that can be observable and measurable. So age, education level, employment status, geographical location. But as we know, individuals, there are some unobservable characteristics that may affect the outcome of interest. For instance, empowerment in our example, empowerment in our example, and we cannot really control these characteristics using the PSM. So the PSM assumes that we will only control for the observable characteristics in order to overcome the problem of non-randomization and to remove the selection bias by keeping observations or individuals, non-participant in the program, who are close to the observations who had been treated or benefit from the program. And I'm saying close because you cannot really find two observations identical. They can be close, but for sure we'll have difference between the different observations. So here the PSM would control for the observable characteristics to remove the selection bias. So as if we are mimicking randomization, as if I want to know what would be, so we assume that we have a group of individuals, and I will randomly select a group of these individuals to benefit from the program, okay? But because we didn't do this from the beginning, so I will say, okay, I assume that they are all have the same observable characteristics, so we'll take someone who benefit and someone who did not benefit and compare the outcomes of these two groups of individuals. Is it clear, the idea?
Excuse me, Racha.
Yes, Hassan.
A question, please. So can the PSM be used over panel data, let's say over 10 years' time, for instance, or is it usually cross-sectional mostly?
Okay, usually we are using for cross-sectional, but you will see on Tuesday when we will study the difference in difference method, which is usually used when you have panel data or you have 2 points in time. In fact, you can combine between both, between difference and PSM, to be able to, because the advantage if you have a panel data that you have the same, for instance, the example of takaful, it was implemented in 2015. If you already have the characteristics of these individuals before starting benefiting from takaful, so in 2014, 2013, and in 2015 and after, so you can compare between them before and after. Okay, this is what
Yes,
we'll do in the different.
usually, preferably, it's 2 years in time, so 2 observations.
Yes,
Okay, thank
exactly.
you.
But the PSM is a way to overcome this if you don't have panel data, and this happens for a lot of studies and a lot of data, as you know. So we will overcome and use this PSM method, but you can use both, as you will see next Tuesday, inshallah. Okay. Other questions? Okay, perfect. So the main question now to be asked, what are these characteristics that we wanted to match the persons with? So for instance, if I will talk about our group, if I want to match by gender, a lot of individuals can be matched together. If we want to match by age, not the same individuals matched by age will be matched by gender. If we want to measure to match by nationality, it will not be the same thing. If we want to match by education level, it will not be the same thing. So the important question, what are the variables or the characteristics, the observable characteristics I would use to match? And which weight I will give to each variable? Why? Or to each characteristics? Because if I match by gender, as I said, for instance, let's take the example of takaful. Takaful is already applied only for women. Women are the ones who take this cash transfer. So if I wanted to match between women who participate from takaful and women who did not participate from takaful, okay, but all women can benefit from takaful. So it's not the best variable or the best characteristics to match. Okay, so let's match by age. But another important factor is geographical location. Another factor, how many children she has. So you see that you have different X's, different variables that you can use to match. But which one is more important? Should I give more weight to age? Or should I give more weight to geographical location? Or to the size of her household? Or in the other example, to the gender? So according to you, or should we match first by age and then by education, and if we have men and women benefiting from a program, so by gender. So how do you think we can answer this question? What is the best way to do this? Any idea, any suggestion if we wanted to match between two different groups by characteristics? What are the characteristics we'll choose and what weights we'll use?
Can we choose different weights and make scenarios?
Yes, so this is supposed to be the idea, and this is an important point, Zara, that we need to check different ways of matching between individuals, because the variables you will choose and the weights you will give to variables can completely change your results. So if I decide to only if I wanted to match only by age and gender and geographical location, it's not the same thing if I decide to match using age, gender, geographical location, household size, and labor status, for instance. So to answer this question, PSM suggests, okay, that we will, instead of matching by X variable, okay, we will match using a single dimension. So as if I will take all the variable x's we believe that can eliminate the selection bias, because these are observable characteristics pre the intervention or pre-program or pre the selection to benefit from this program. We know that these characteristics affect the intervention of the program and affect the outcome we are interested in. But I will take all these x's and put them into an equation to get one single dimension or one single score, which is px. And this is the main idea behind the propensity score matching. So I wanted to give a score for each individual, for each of the individuals we have, the participants and the non-participant. I will match between them, we'll see how, and then I will compare the outcome. So for instance, assume that in 1 year, ERF wanted to see the impact of this training on publications of researchers who benefit from it. So we'll try to match you with a group of individuals who have similar characteristics using the propensity score. So we'll include education, age, gender, geographical location. We get this px value. We match between you and those who have close p-value, but they did not participate in the program. So this is our treatment, the training, this applied micro-econometric training. And then, so we'll match between each one of you and someone who is close and see, for instance, the publications. If you publish more than the other person who didn't benefit from the training, so we can see that, okay, this training has a positive impact on the publications and it was beneficial for the trainees. But the question is that instead of taking each x alone or not being sure which variable should take more weight, we will include them in one equation and we will calculate the propensity score and then match to the closest one. And again, I'm saying close because you cannot really have two observations that are identical. They will be close in values, as we'll see how we'll match between them. But it will allow us to eliminate the selection bias, the best we can do given that we have cross-section data that is non-randomized. So this score or this px, how we calculate it, is simply a probit or logit model. Do we all know what is the probit or logit model?
Yes. Yes.
Okay. So the main idea of the probit or the logit model is that our variable y, our dependent variable, is not a continuous variable like what we are used on with the OLS. It's a binary variable that can take 1 or 0. So we want to see the probability that we are in this status, that our variable taking 1. So here I wanted to see the probability that the person is treated or is benefiting from the program, for instance, takaful, equal 1, 0 otherwise. So I will have the beneficiaries and non-beneficiaries. And X are the variable that are pre-exposed of, or the characteristics before getting benefit of this program. So again, I will collect all the variables that we think, we believe, and we know from the literature that they can affect the selection into the program and also our outcome. And as I mentioned, our outcome can be empowerment, labor outcome, income, and we will estimate a probit or logit models, and I will give a value Px estimated for every individual, for those who benefit from the program and those who did not benefit from the program. Okay, then we start matching. So I will match someone if two P values are close, but one benefit and one did not benefit. I will match between them, and I will compare the outcome variables between the two observations. If the person who is treated have higher value of the outcome, so we can conclude, and the difference is significant, we can conclude that this program has significant positive effect on the outcome variable. If women who are benefiting from takaful has higher decision-making power inside the household compared to those who were matched with and did not benefit from takaful, so we can conclude that yes, program of takaful empower women and give them more decision-making power inside the household. So the steps, I will select the variable axis. We will estimate our probit or logit model. It depends. It will give us similar results. We will match between both according to the distance between each treatment observation and the control observation. Keep in mind that Px is not is continuous quantitative variable. It will take values from 0 to 1. So this is why we are trying to minimize the distance. So we'll select or we'll match between the observation who is treated with the observation that is not treated, the closest one, given the score. How we will choose this match or how we will specify the distance, we have different methods that we'll talk about. The outcome of each treatment, so this is what I was just mentioning, just for your information, and this will be the second part of our lecture, which is Stata. Stata, in fact, make all the steps for you in one. So the command is one sentence, and Stata will do all the steps for you. So you just specify to Stata that these are the variable axes. This is my variable outcome of interest. I want you to match using this method, and Stata will do all the steps. Will calculate, will estimate the probit or the logit model, will give you even the results of the probit or logit model, will match between the treated observation and the control observation, will provide you with the average treatment effect in the treated observations and in the untreated observations, and will compare between both and tell you if it is significant or not and positive or not. So it's one sentence, but you need to understand the steps, because as you will see now when we'll discuss, and as you will see when we are doing the results, when we are doing the Stata part, that whatever thing you change, it can change your results. What variables you are including in your X variables can change the results. What variables can, sorry, what matching method you are using to match between the observations can change the results. And this is really important that you try several several matching methods to be sure that all the variables you are including in your X are important one to control for or to try to remove the selection bias, to be sure that your results are really robust and the effect is correctly positive or negative or not significant. So for instance, if I include age, for instance, if I wanted to measure the impact of a given treatment training in the labor market on participation of the youth population. If I include all variables and I did not include the gender, okay, which is, as we know, in our region, female have the lowest labor force participation, and women do not participate or don't have the same opportunities as men. So if I exclude the gender, which is important factor in or important variable affecting our outcome variable, which is labor market status, and at the same time can affect the selection into the training. If I ignore this variable, so this is an important pre-intervention variable, an X variable that can affect my outcome and the selection to the treatment. I did not include it in my X. variables, it was not included in my model, it can change completely the results. So we need to be sure that all x's, especially, and as of course you discussed with Dr. Chahir yesterday, we need to be sure that your error term is, the expected value of your error term is 0, that your variables are exogenous, you are sure that you did not exclude any variables that can affect your outcome and can affect the participation in the program. So you have to be sure of this, and you have to try several matching methods, because based on the matching methods, you can have different results. Of course, if your model is correct and is robust, and you have all the variables x's affecting your results, whatever matching method you will apply, whatever way you are using to match or to measure this distance between the treatment observation and the control observations in the neighborhood, you should have the same conclusion. So if the careful program in the first model with the first matching method, we found that it has positive effect on women empowerment in Egypt, if you use the matching method, you should have the same results if your results are robust and your x's are correct. If you start having different results, one time takaful has significant effect, positive effect, in another version of the model with other matching method, takaful is not significant positive, you have to know this kind of alarm that there is something wrong in your method. And this is why you need to be sure that your x's are all included, and you need to be sure, I need to try or to estimate the model with different matching methods to be sure that your results are robust. And we'll see how we'll do this when we'll use STAT. One important thing is that, and also in the selection of x's, you know, if again, I will take our example. If we wanted to match with based only on gender, we can have a lot of matches, no? Because by gender we have, we are not 50-50, I think, but I can be matched with all women who are in the training. If we match by age and by gender, we still can have several matches, no? Because it's common that you will find different persons who have same gender and same age. So the less variable x's you include in your model to match between persons, the more match you will find. Okay, and this will not be very specific, because just age and gender are important factors in women empowerment, but you have several other variables that can affect women empowerment, like education, labor status, geographical location, household size, parents' education. So if you only include 1 or 2 or 3 variables, yes, you are sure that you will get a lot of matching, but they are not as precise as you include more characteristics. Because imagine, again, keep in mind, it's the idea as if I am trying to have someone that looks exactly like me, has the same characteristics as me, but did not benefit from the program. So I can compare between my empowerment and her empowerment. And if there is a difference, because we have common characteristics, so we can say that my empowerment is due to the takaful program or to this training I got. So the less characteristics you include, the more match you will have, but it will be less precise. On the other side, if I want someone exactly like me, so I decide to include all x's, age, gender, geographical location, parents' characteristics, husband's characteristics, number of children, education level, years of expertise or training. If I include a lot of x's, it will be difficult to have matches, because how many persons in the sample would have exactly the same characteristics as me if I include all these characteristics? We can have 2 or 3 persons who have same age, gender, education level, geographical location, but are we sure we'll find 2 persons who have all these characteristics? In addition, same husband characteristics, same parents characteristics, same children number. So here, this is the dilemma, or the time you have to spend to think clearly what are the variables you wanted to include, to be sure that you are creating your counterfactual group to match it with the treated or beneficiaries group, but in the same time, not too many X's that you are not able to match between them. And in fact, if we look at this graph, so you have the density of the characteristics of the non-participants of the P-score, and here you have the density for the participants, and you need to have a common area. So based on this common area, so based on this blue area, I will start. So in this area, you have beneficiaries, and you have also non-beneficiaries. Okay, so this is a common support of the score, of the P-score, of the participants and non-participants. And now I will compare. So I will compare this one with this one with this one, or with this one. It will depend on which matching method we will use. So you need to have your common support area of the P-scores large enough to be able to match between the individuals. So you need to include enough X's to have this common support, but not so large that you can compare between two persons just because she is 25 years old and she is 25 years old. But maybe these two persons, one have a PhD and the other one has only primary education. So if you compare between them, I mean, assuming that one who has a PhD also is benefiting from this TACAFL program. So you will say, okay, the beneficiaries of TACAFL, for instance, the one who has primary education is the one benefiting from TACAFL, and the one who has PhD is not benefiting from TACAFL. If you compare between them only based on age and gender, so, and you find that women who are beneficiaries from TACAFL are not empowered as the other one, here you are not, I mean, for sure, it's not because of TACAFL, it's because the woman who is benefiting from TACAFL has only primary education, and the one who is benefiting from, not benefiting from TACAFL has a PhD, assuming that education empower women, which not the literature is not really showing that this is the case. But again, here you are excluding an important variable that can affect empowerment, your outcome variable. And if you don't include it, your results will not be correct because you will assume that TACAFL is not empowering women, which in reality, when you compare this woman of 25 years old with another woman who have the same level of education, you can find that, yes, she is more empowered compared to her due to TACAFL. So this is important to choose a variable X's to have a region common of support that is large enough to match and to find adequate comparison group, but in the same time, not so large that you are not really sure about your results or the comparison between the two groups. Is it clear? Are you following? Am I going too fast? Everything is clear?
Yes, it's clear.
Perfect, thank you. Okay, so this means from all what I said till now that your results, your estimates of the treatment impact, keep in mind our question, I want to know if this program, this training have a significant impact, positive or negative, on a specific outcome, yes or no, in a non-randomized sample. And I'm using the PSM, trying to estimate this treatment impact while controlling for the observable characteristics in order to eliminate this selection bias that resulted from the non-randomization. But your results will depend on, again, what are the variables you are including in your model to estimate your propensity score, and how you specify this equation, and how you match between observations. So you need to be sure that these two questions are correctly answered. You need to make robustness check by trying different estimation, different matching methods, and being sure that all variables are included to be able to make sure that your estimates of the treatment are correct. Let me ask you, so I mean, I'm giving the example of women empowerment because this is my research interest, and I'm saying these variables because I know from the literature that these are the variables that can affect women empowerment and in the same time affect the selection to programs as TACAFL. But in general, if we have any other outcome like poverty, for instance, or health, nutritional status of children, or years of education of children, and I have other cash transfer programs or social policies or other social policies programs, how do you think we should select variables X? On what criteria we should depend to be able to select the variables X? Any thought, any suggestion? I want to hear from you.
Can the characteristics of the treatment group form the base for choosing these variables?
So you mean the characteristics that of the treatment group, or I mean of the training itself or of the programs itself?
Of the treatment group, the women that are included in the CAF, or maybe they can form the base for our variables.
Yes, but what variables? I mean, why we should choose, and not only for this example, in general, if you wanted to select the variables X, observable variables that you want to use as a way to match between participants and non-participants. You
I
will
would
depend on
search for literature that are on my topic, and then I will choose based on them.
Exactly. So one main thing is the literature. We see, for instance, for women empowerment or for poverty status or for nutritional outcomes, what are the variables that can affect this outcomes in the literature? Other ideas, how you can select this axis?
I mean, of course, there can also be unobservables that affect the way in which women get to be in the treatment group or not.
Exactly, Hassan. So there are other unobservable characteristics, but PSM would not allow us to control for it. And this is the main weakness of PSM, that we should use characteristics that we can observe, we can measure, and we can compare individuals together based on this observable characteristics. The unobservable characteristics, we cannot control for it using the PSM. We will see it in the difference next Tuesday, that we can control it when we have again several rounds. But you are right, I can control for age, education, gender, geographical location, husband's characteristics, parent characteristics. But at the end of the day, each woman has different unobservable characteristics. Maybe a given woman have more willingness to be empowered, like to participate in the decision-making process, while another woman is not the case, even if they have both the same characteristics. But unfortunately, in the PSM, and this one weakness of the PSM, you cannot control for the unobservable characteristics.
Excuse me,
So,
Rasha.
yes.
Just a clarification, please. So if we can use difference and difference, why do we use PSM in the first place?
Again, if you don't have the data that you can use difference and difference. Difference and difference, you need to have 2 points in time for each observation.
It makes sense.
But if you don't have it, you know, it's always, I mean, a lot of techniques that you can use are good, but it all depends on the data, if you have the data or not. And many programs, I mean, in development, and a lot of social policies programs that we wanted to measure its impact on poverty or nutritional status or women empowerment, a lot of programs, we don't have a national representative baseline survey. So if I will take the example of poverty, for instance, or the nutritional outcomes, usually everywhere and in our region, we are using the household income expenditure and consumption survey to calculate the poverty status of the households. We can also calculate variables related to nutritional status. We can also, I mean, women empowerment, no, it's not in the household expenditure survey. So this survey is conducted for Egypt and for other countries in the region each 2 years, okay? But you are not following the same persons over years. So each year you have new individuals. So it's cross-section. And if I wanted to know, for instance, if individuals who are benefiting from takaful move out from poverty or not, I cannot, I mean, this family X or family A that I am observing in 2024, are not the same family that I observed in 2022. So I cannot say, okay, that between 2022 and 2024, the female of this family benefited from takaful, and now she is out of poverty. So I can conclude that she is, this family is better off because of takaful. Because I don't have the characteristics of this household over the years. I have each 2 years, national representative survey, but not panel. And this is why, and it's not because I am teaching I am giving this training at the ERF, but really the Egyptian labor market panel survey, the panel data provided by the ERF is really like a treasure, because you have same individuals observed over the years. You have the progress of their education, employment status. So you can observe the same person or the same individuals, how they evolve over the years. You can compare between their status before specific year and after specific year. So you can use diff or other methods. So this is why panel data is important, but it's not always available for all the surveys. And this is how we can overcome this. So usually when you are using PSM, you declare that you know that one of the weakness is the unobservable characteristics, but it's the best we can do given the availability.
And we use some factor analysis to include some unobservable variables. To combine PSM with some factor analysis, such as personality or something like that.
But what do you mean by factor analysis? How you can control for personality, for instance, in this case?
I mean that can we, let's say it's a factor, and then we include it as an X in the model.
If you can measure it.
Yes, can we measure it something like Likert scale or and structural equation modeling, something like that?
I mean, no, some X's cannot be measured. For instance,
Yes.
my ability of taking decisions. I can be someone who is empowered and I can take decisions even if I'm illiterate and I am young. And someone else who has a PhD and she is older than me, maybe she doesn't have the ability to take decisions. So this ability, it will be difficult to measure. This one thing. So first, there are some unobservable characteristics of individuals that cannot be measured using the surveys that we know. You cannot ask someone, do you have the ability to take the decisions? Or let me give you an example. For instance, empowerment. Usually, we don't ask, how you measure empowerment is a huge question, no? Because I can feel empowered, though I'm not empowered at all. And I can feel unempowered, though I am empowered. So usually we ask questions that will be proxy for my empowerment. If I am taking decisions or not, if I can go out of my house and have freedom of mobility or not. So some variables you cannot really measure it or observe it. The other thing that maybe it can also exist that there are some variables X that are observable and you know that it can be measured, but your survey did not include this X's. Okay. For instance, assume that, and this also the literature shows us that parents' characteristics can affect women's empowerment situation. If I am born for highly educated parents with an employed mother, most probably I will be more empowered compared to someone who was born for illiterate parents and the mother is not employed. Okay, so we know that parents' characteristics can be a variable X that can affect our outcome variable, which is the women empowerment status, and can affect because it would affect her employment status and it can affect her income. So it can affect the probability that she will be benefiting from takaful or not. So we know that parents' education is an important factor. We can observe it and measure it. I mean, this can be something we measure. But in the survey of the household expenditure, for instance, we don't have this variable. So even if I know that this variable is observable and I can measure it, but I don't have it in my survey, in this case, I will not be able to include it in my X. Okay. But here we assume that we have all the required observable characteristics in our data set. However, we are aware that there are unobservable characteristics that we cannot observe and we cannot measure and still can affect my outcome and my treatment or being selected in the treatment or not. Is it clear?
Yes, thank you.
Okay, so how can we choose our variables X? As we said, any variables that can affect program placement, so being selected into the program, or in other words, that can affect the fact that T equal 1. So this means that I am selected in the program, including the pre-intervention level of the outcome. So also this is important. So I have the outcome variable is Y, okay? I want to choose X that affect Y and in the same time affect the fact of being treated or being placed in the program. One of the variables that can affect Y can be the income level. For instance, assume that I wanted to measure the impact of a specific training program on the income level of the individuals. Just let me turn on the light, sorry. So I wanted so my outcome variable is the income, okay? And T equal 1 is a specific training. I will give it to individuals and we assume that this training would increase the income of individuals. Of course, the variables that would affect income level and being placed in this training, again, can be age, gender, education level, geographical location. I don't know if the treatment, for instance, the training is about artificial intelligence. So maybe persons who are selected would be persons who did engineering, for instance. So also the education, what type of education can affect if you are placed in this treatment, in this training program or not. But one of the factors also that can affect my Y income and the fact of being placed in the program is my income in the year T minus 1. Okay, so maybe I need to know my income in the last year and we know that it can affect my income this year. So one of the variables that can be included in the X in addition to the observable characteristics that we know, it can be the pre-intervention level of the outcome variables, because maybe the fact or the criteria to be selected in the program to get this training is that you have a specific level of income. So in this case, we know that the income of the pre-intervention level of income can affect my actual income, my actual outcome variable, and also being placed in this training program. It can sometimes be interviews if it's a new thing or new treatment or new program. So we can make interviews to discuss with the participants and non-participants, trying to see what are the factors that affected the intervention in this, the being selected in this program and this outcome. And of course, as we mentioned in the literature, and if we cannot find good observable variables to explain who participate and who does not, here we are doing a bad job in eliminating selection. So assume that we couldn't find, so maybe gender is not the one variable that affect being selected in the treatment program and my outcome variable, which is the income, and not the age. So I'm already excluding 2 variables, and not years of education. If we are not able to find enough variable X's that can explain why selected persons have benefited from this program and why others did not benefit from this program, so we'll have a problem in matching, or will be doing poor job in matching between the participants and non-participants. And in this case, we will eliminate the selection bias, because the selection bias comes from the fact that these observable characteristics can affect both being treated and my outcome variable. And I wanted to exclude this by comparing between 2 individuals, equal, same characteristics, but they have been different in one thing, being treated or not. If I'm not able to do this match because I cannot able to find what are the correct variables to match between them, I will be doing a poor job in eliminating the selection bias, and we'll have the biased effect, as Dr. Chahir shows you yesterday, that the expected value of the error terms is not 0, and in this time we'll have the value of the coefficient beta 1 plus something. So my impact of this program or this training is not really correct, is not efficient. So this is important to consider. Why? Okay. Now the question, so the first step is to choose the variable x's. We enter the variable x's in the in our equation. We estimated using probit or logit, and we got the p-scores. Okay, and I will show it again. Stata is doing all this in one step, but I will show you the results for each step. So, okay, now I have the variable, the values of px. How can I match? How can I say that the closest observation to Racha is Nadine? How can we say that it's Nadine and it's not Dalia? Why Racha is matched with Nadine and not matched with Dalia, while Dalia and Nadine did not participate in the program and Racha participated in the program? How can we do this match? So because px is a continuous variable, we know that no two observations will have the exact estimated score. And this is why in the definition we are saying we are matching participant or treated group with non-treated observation, the closest one. Why the closest one? Because this is continuous variable. We are not sure we have two exact estimated. So I will if px is 0.08 for Racha, I will not find another observation that is 0.08, but I may find an observation that 0.075 or 0.069. So how we choose this, and again, this we are not doing manually, we have thousands of observations, we need to find a way to do it automatically. We will check a couple of methods, but we'll simplify into two groups of methods: simple matching methods and more complicated matching methods. And again, as I mentioned, when we are estimating, and we'll see it in the second part of today, you need to try with different matching methods, because you can have that takaful is amazing, it's significant, it's empowering women using one of the simple matching methods, but when you use another method, it's not the case. And as I always said to my students, assume that tomorrow will be asked by our ministers as researchers, please tell me if this program is benefiting really women, and should we continue apply this program or not. If I will do my exercise and I am not sure about its robustness, and I'm saying yes, takaful is amazing, it's empowering women, you should continue doing this program, you should give it to more women, and this is not the case, so you are not giving good recommendations. So you need to be sure that your results are not related to your matching method or to your variables x. You need to be sure by trying several matching methods and see if the results are all the same or not. That in all matching methods you have the training or the program have positive significant effect or negative significant effect or significant or not significant effect. You need to be sure of this. So what are these methods? The simple matching method will see two ones: the one-to-one matching and the nearest n neighbors. So the one-to-one matching, as it says, I have this observation, I will match it with the closest one. My observation gets a value of 0.05. I will find the closest one to the 0.05, which will be 0.038. This is the closest observation using the one-to-one matching, or it can be 0.051, or it can be 0.052. So we have, I'm saying a lot of, so here we have the p-values. Okay, so here we have participant 1, here you have non-participant 1, here you have participant 2, here you have non-participant 2. Okay, so now we wanted to match using the one-to-one matching. So it's simple. I will match P1, this participant, with the closest non-participant. So the closest non-participant, given the values of Px, is person 1 with this one. So I will match these two together. Okay, this P2 already we can see that we don't have a lot of close observations to P2. But this one is the closest, even if it is far. I mean, all this is difference, but still it's the closest observation. We can match it together. Okay. Now, assume we have, yes.
Hello, Mrs. I don't understand what you mean by distance. Distance of what? Between participant and not participant.
Yes, so distance is the value of px. Okay, let me just 1 second. Let me show you something on SATA.
Great.
It may clarify what I'm trying to say. Let me share my screen. Okay, this is a database you will be using. Okay, it's an extraction of the ELMPS 2006. So here you have different individuals, and our outcome variable will be the labor market outcome, as we'll see. These are the observations. Let me just trying to clarify the idea. In these observations, we have some participants and some are not participants. Okay. What we are doing when we choose the X variables and we estimate the logic model, it will estimate for each individual a value, a P value. Okay. So this first individual will have decided Px equal 0.01. This one will have 0.02, whatever. So if I return back to the PowerPoint, so assume that this is our line, our column. So here you have the individual, okay? 1, 2, 3, as the one I show you in Stata. We estimated our probit or logic model, and we got a value of the Px, okay? And close to this line of individual, we have the treatment. So first individual was treated, the second one not, the third one not, the fourth one was treated, the fifth one also was treated. And when I estimate my probit model, I got a score for each individual, if this individual is treated or not treated. So here, let's assume 0.7. Here is 0.65. Here 0.2. Here 0.64 and 0.75. Okay. What these scores mean? This score means that this first individual, given their characteristics, they were supposed to be treated or participate in the program with a probability of 70%. So given my characteristics that I included, assume I include in the X, we have age, gender, years of education, okay, geographical location, and assume we have parents' education. So given these 5 characteristics, the first person was supposed to be selected in the program with a probability 70%, okay? And he is really or she is really selected in the program. Assume the program is a training for the labor market. The second person, given her age, gender, years of education, geographical location, and her parents' education, she was supposed to be selected in the program by probability 65%, but she was not selected. So if I compare here, or if I want to try to match here between an individual who participated in the program and an individual who did not participate in the program, I can match these 2 individuals. They have the distance between both, the difference in the Px is not so big, it's the closest one. It's not the closest one because in the rank by coincidence, this one is this 2, because it can be, for instance, the individual number 6 who was not selected is 0.75, for instance, and here it was 0.45. So here's the first one can be matched to number 6, to the sixth one. Okay, these two persons can be matched because given the characteristics I include, the first one had a probability of 70% to be selected in the program, and she was selected. And the sixth person had the probability to be selected in the program 75%, and she had not been selected. So here, as if I am mimicking the randomization, that two persons have similar characteristics because given their characteristics, one had the probability of 70% to be selected, and the other one had the probability of 75% to be selected. However, one is selected and one is not. So the closest one, given the values of Px, I am comparing the values of Px to match between the individuals together. So here, what Stata is doing, that, okay, this one is 0.7. I want to see what are other persons who are not benefiting from the program, but has a value of Px close to this 0.7. From all this one, they found this observation. Okay? Here, 0.664. What is the closest one that is not participant and have a value Px close? Of course, 0.2 is far, 0.45 is far, even 0.45 is not close, but still it's the closest observation we can observe. So what I'm doing about this instance is that I'm giving a score for each one. This score tell me the probability that this person would have been selected into the program I want to measure its impact. However, this person does not had been selected or had not been selected, so I will match between them according to the value of the P. And this value of the P, you need to find the closest one. So the closest one in distance, which means the difference between this P value and this P value is close and not far. I don't know if I answered your question, Tani, or I confused you more.
Thank you. Thank you, Mrs.
I handle.
Other questions?
Just wanted to check about something, Rasha. So usually,
Yes.
when Stata chooses the matching, when it does the matching process, how close should the p-values be? So is there any criteria for that?
Yes, so this is a good question, Hassan, and this is what I was about to say. So in fact, you have to specify to Stata which matching method you will use, the one-to-one matching or the nearest and neighbors or whatever. However, one-to-one matching, as we saw, if I will assume I am organizing my values of Px horizontally, this participant number n, okay, the closest non-participant, the closest non-participant to this participant can be here. So here is non-participant who has a P value close to the person B, and it can be not here, it can be here. In other words, that the P values can take value between 0 and 1. So the participant here, his value was 0.4, and the closest one is 0.7. The difference between 0.4 and 0.7 is large, but in the middle, there was no non-participant that has a value closer to the 0.4 than 0.7. So you can ask Stata to match whatever is the closest one. So Stata can take from 0.4 to 0.7. So Stata will match these two individuals. Or you can specify to Stata a caliber. A caliber that you would ask Stata not to go further than 0.01 as difference, for instance, or 0.1 as difference. So in this case, if I specify to Stata that you need to have maximum distance or maximum difference between the Px of the participant and the Px of the non-participant, if you have more than 0.1 as distance of difference, you should not really match between them. The problem here is that if this poor individual who is participating in the program and the only one who has close value to his value of Px is 0.7, if you specify the caliber, this person will be dropped. Why? Because you say that, okay, you need to match each observation with another observation that is not participant and has a close value of px, but it's not far than 0.1. So it can be dropped. So you have to choose or to leave it or to specify a caliper. So this caliper is like a tolerance level. You don't accept that you go further than this. And you can try both, of course, to see. The other thing that you try not to match the individual with the closest one individual non-participant, but with an average of close observations. So I compare the p-value of Racha with the p-value of the closest n, let's say n equal 5 persons. So I will compare the outcome of Racha, who participated in the program, with the average outcome of 5 persons who have values of px close to the p-value of Racha. I will, in 2 minutes, I will show you the equation that may make it clearer for you. The more complicated matching method is the kernel matching method, and the kernel matching method is a non-parametric method. So it's kind of estimator. You use it and you use weight average for all individuals in the control group. So in the simple one, you can match one observation with one observation, one participant with one non-participant. You can compare, when you use the nearest n observations, one participant with the average treatment of 5 participants or 4 participants. You decide the n as you want. And each time you select the caliper or you select an n value, you can you change your results. So this is why I'm saying you need to try several ones to be sure that your results are robust to whatever parameter you are changing in your method. Or you can decide to use a weighted average of all the individuals in the control group to construct a counterfactual outcome. So Racha, I will not compare the value of the outcome of Racha with the outcome of the closest one who is not participating in the program, but has a p-value close to Racha, px value close to Racha. Or I will not compare the outcome of Racha with the average of 5 closest observation to Racha. No, I will take all the control groups, all the individuals in the control group, in the counterfactual group. I will calculate a weighted average, and I will compare the outcome of Racha with the outcome of this constructed counterfactual outcome. And it make a difference. When you calculate my income with the income of the closest observation, it's not like you compare between my income and the income of the closest 5 observations, or you compare my income with the weighted average of the 5 of all the counterfactual observations. And what I mean by close, it depends on the difference of the value of px of Racha with the px of all the other observations you want to compare. And the weights in the kernel method, matching method, is depends on the distance between each individual from the control group and the participant observation. So you will give weights for each individual in the counterfactual group, depends on the distance or the difference in the value of the px between this observation and the participant or the treated group. And also you have 2 parameters to select when you use the kernel method. You have different options in SATA, which is the kernel function, how it looks like, and a parameter that is called bandwidth. Let me show you this in terms of of equation. So the idea, I wanted to calculate the average treatment effect, okay, of the individuals who benefit from a specific program. Why is the outcome variable of individual G if the individual G have been treated minus the outcome variable of the individual G if she was not treated or he was not treated? Control. So I cannot observe the same person treated and non-treated. This is why the idea, I wanted to have the observations of the treated persons, and I will subtract the observations of the outcome of the control person, and the difference between both, I will take the average. Then I will say, okay, this is the average treatment effect of my program. Again, assume I wanted to measure the effect of takaful on on years of education of children. So I will take the years of education of each individual who is treated minus the years of education of the children of women who had not been treated, which I call them control. And the difference between both, I will calculate the average based on the number of the treated individuals, the number of women who benefited from takaful. And this average treatment is the effect of takaful on the number of years of education. Okay? The question that we were trying to answer from the beginning, how you choose the control observation? Because this is the counterfactual observations or control observations who are supposed to have the same characteristics as the treated observation, but they had not benefited from the program. If you use in this case here, you are using the closest one. So if I return to my stata, assume this individual I, okay, the closest one who has a value of px close to this person is this individual, number 410 at the end. So this one, number 13 in line 13 and in line 1, they are both matched together. Why? Because the difference in their px values are close when I am using the closest observation. So I will calculate the difference between the outcome of this variable and the outcome of this variable. Then I will do the match for all the other participants, and it will show me the difference between all the treated and all the control group, and I will add it and calculate the average. Other method that I can use, as we said, instead of making the difference with only one observation as control, I will take the average. So I will calculate, I said, okay, I will compare the outcome of the individual I who has been treated with the outcome of the closest 4 individuals. I will check 4 individuals, or SATA will check 4 individuals who have a value of px close to our treated person. We'll calculate an average of this. And so you see, CI, each individual in this group of CI, which is the minimum distance between the value of the px of individual I and the value of px of individual G. So individual I is my treated person, the person who benefited from the group. I will calculate the difference between its p-value that I got it from the logic model with the p-value I got it for the other who are not participants, and I decide to take, let's say, 4 closest observation or 3 closest observation. I will calculate the average of their outcomes. So here is the income of the women I who benefit from takaful, and here is the average income of 4 women who did not benefit from takaful, but they have close value of the px close to the px of women I. And I will calculate the difference, and I will divide by the number of beneficiaries. Here I got the average treatment effect using the nearest n neighbors. Okay? Or I can use this kernel method, which is, as you, I mean, I don't know if you're noticing or not. I hope you are noticing. So here we start from a sample control value, which is the closest observation who is not treated but has a p-value close to the p-value of the treated person. Here we try to complicate it more by taking a sample average of the control of the outcome of the control observations. And here I will take a more complicated average using the kernel method. So the G function is a G function, the kernel is a kernel function, and this parameter Hn is the bandwidth parameter. There are default values in the in stata. You can choose between them. And here you can see that the outcome of the individual G who is not treated and has a p-value. No, here is not a p-value. Here you have all individuals in the control group. So you decide to take an average of the outcome of all individuals in the control group using a bandwidth, using a kernel function. And kernel function depends on what? On the distance between the p-value of the observed and the p-value of the control group and the p-value of the treated group. So here you make it more complex because you wanted to compare the outcome of your treated person not with the closest one or the closest 4, but with an average of all individuals who exist in the control group. And the weight here would depend on what? On the distance between each observation in the control group and the observation which of the individual treated. I hope it's clear. Should I consider the silence means yes, it's clear?
Yes, all clear. Thank you.
Oh, okay, when we'll do stata, I will show you these p-values, how they look like. I mean, again, all the work is done by stata by matching between them. But again, keep in mind the idea that we are creating a p-value for each observation, shows me the probability of being selected into the program. Whatever my actual situation is, I am selected or I am not selected. And then we can match according to this.
Madam, sir, Mrs. Racha,
Yes.
actually, I want to know when we should use the simple matching method, when we should use the kernel matching method, and if we can say what is the importance of using such method, the application, I mean, when and why we should use it.
Okay. In fact, you should use all of them. Because again, if you change your matching method and you have different results, this means that your results are not robust. Let me try to to simplify. This is the individual I, okay, who is treated. She is a woman benefiting from the program. Okay, I can matching with one woman here, the closest. So given this match, I will decide that the treatment increase women empowerment. Okay, but I can tell you, so you told me, okay, I use the closest observation and I found that the treatment, this training or this program increase women empowerment, so this is a good program, we have to do it again. But I will tell you, okay, have you tried, instead of comparing the outcome of this woman with only one, to compare it with an average of 3 women? Because maybe this closest person, this closest one, the difference, if you choose the caliper, if you don't choose the caliper, the difference was so far. So I told you, okay, instead of compare one person with one person, it's better to compare one person with the outcome of this woman who benefit from the program with the average outcome of 3 persons. If you find when you use this match that this treatment or this program significantly increase women empowerment, so I don't know why I'm doing euro, it's like women empowerment. So okay, if the 2 methods are saying the same thing, so this means your results are robust, that this program is really increasing women empowerment. But I may tell you, okay, let's not do this, because maybe, the 3 persons are the closest to this one, but for another observation is not the case. So let's match this person with an average of the outcome of everyone in the control group. So instead of taking the average of 3 observations only, I will take the average of everyone in the control group using kernel method, and I will compare with. If also this give you the results that this training increase women empowerment, this means you are doing a good job, your results are robust, whatever the match. So your results are not depending on how you match. Because simply when you match this first woman with this one, is not as you match her outcome with the 3 others or with everyone. If you usually, I would recommend that you use at least 3 methods, because notice that even within each method you can change something. Here you can put one time caliper and one time you don't put caliper. Here you can do the average with the closest 3 or the closest 4 or the closest 5. Here you can change the kernel function and the bandwidth parameter. So at least try three methods. If the three methods give you the same result, so you are good, there is no problem. And this we'll see in one of our examples, that you will have two methods giving you one result and the third one not. But at least 2 from 3 tell you that there is positive effect, significant effect, so it's okay. So my recommendation is that, I mean, if you use a very simple, it has its drawbacks, yes, but its simplicity. If you use a very sophisticated, the kernel one, also it has its drawbacks, so it's better to use at least 3 methods. You can use the same method by change. Instead, for instance, of using the closest 3, you choose the closest 4 or the closest 5, and you compare. If 3 of your results still use the same things, or 2 from 3 of your results still use the same thing, this means that you are doing a good job, or your results are robust. But there is no one method that you can use and be sure that, because this matching, it really depends on the values of P, and it depends on how SATA will match with this. For instance, why should you assume that, for instance, Nadine and Rashida and Rasha, they have close p-values. Okay, I have 0.7. I am the participant. Rashida have 0.65, and Nadine have 0.75. So they are both close to me in terms of p-values. They are both not participating in the program. If you match me with Nadine, maybe the results will not be the same thing as if you match me with Rashida, even if both are the closest to me. So here's a solution. Instead of matching Rasha one time with Nadine, or I don't know if it's Rashida or Nadine that I will be matched with, so it's better to say, okay, let's match Rasha with the closest 3 observations. So in this case will be Rashida, Tahani, and Nadine. Okay, so this is why the matching is really important, and to be sure that it's not how you choose the closest observation affecting your results, it's better to have different matching methods and compare with.
This is Racha.
Thank you.
I have a question. Based on our experience, do the 3 methods often yield the same result?
No, Abdullah, can you repeat again, please, because your voice was not clear?
Yes, based on my experience, do the 3 methods often yield the same result or give a contradictory result?
I mean, usually it gives the same results.
Yes.
Unless I am doing something not good in the X's I choose, but usually it gives you the same results. And if not, it will be only one that will be different results. So I will take 2. So this is why I am always recommending to try 3 methods. And at least if you have 2 from the 3 giving you the same conclusion that this effect is positive or negative or not, you keep it. But usually it gives you, if you are doing good job in choosing the X's, you should have the same results.
Okay, thank you.
And this is why it all really depends on the selection of your variable X's. What are the variable X's that can affect your results? Okay, some notes. Again, the idea of the effect of treatment on outcome is non-parametric, but it depends on your parametric choice. So your logit or probit, what variable X's you include, what matching methods you include. So this is really important to consider. Sometimes, so this is the same thing. No, sometimes just I want to clarify here things, but again, this depends on the variable X's. That sometimes you wanted to include, for instance, interaction. So you include age, geographical location, gender, and maybe you also include the interaction between geographical location and gender. But again, this is in the idea of what variable X you can include, and this both can affect your results. And this is what I had been saying, that you have to use several times or use several estimations using different methods to be sure that your results are robust and reliable. One of the things is good to do, and again, Stata is doing it, but you need to check it. You want to be sure that your match is good, that this group of individuals who had been treated and this group of individuals who have not been treated, they are close to each other and they are similar, given the X's you include in your method. To do this, usually we use a t-test to calculate the difference in the means of the covariance between the two samples. So I will compare the mean of age between the treated and the control group. I will compare between the means of years of education between the treated and the control group. If all your T statistics are not there is no significant difference between the means of the control and the means of the treated, this means that you are doing a good job. Because if we assume that the two groups are similar, there should not be any significant difference between the average variable of x is here and the average variable of x is here. No, if there is a significant difference, this means that you are not doing a good job, or this variable is not good in matching. If I found, for instance, that the average years of the participant is bigger than the average years of the non-participant, this means that your two groups do not have on average equal age. So maybe the difference in your outcome is not related to the program, it is related to the difference in age. So this is important to test. And if you find any variable that has a significant difference between the average of the treated and the average of the control, you should change it, or you should consider to see what is the problem. Again, this would bring us to the idea of the common support area that should be large enough to do the matching, but not very large that you are not sure if the effect is related to your program or to any other factor or variable X that is observable, but you are not controlling for. If it's not observable anyway, we are not controlling for, as I said, it's weakness of this method. And this is what I was saying. If I try to include all variable X to trying to find a really very close sample in terms of characteristics, here we are not sure first that we find enough matches, and this can affect the efficiency of your model. It's good to have a lot of X's, but not so much X's that you cannot really find a lot of matches, because also you lose observations and you will not be able to match all your participant to non-participant. One thing you should take into consideration as well, the propensity scores are predicted. So we have like first step that we estimate a probability or logic model. We have the estimated value of the probability of being selected, which is Px, and it has an estimated variance. Okay, then we use the scores to match and to estimate the treatment effect. So here, your estimates are based on another estimate who has a variance. So in this case, you need to be sure that it's like the standard errors or the variance in the predicted propensity is not affected your result as in the treatment effect. You should correct for this. And to correct for this, you have to do bootstrapping. So again, you have a sample with variation, like the normal sampling variation. In this sample, you take it. You estimate first a probability or logic model. So you have your predicted P axis, the probability of being treated, which has a variance. Then you take this Px or this propensity scores to estimate your average treatment effect. So this means that the average treatment effect can have a large variance because there is a sampling variation that already exists in the sample, in addition to the variance that exists from the estimated propensity score. So this can make that the average treatment effect has large variance. So to correct for this is to do bootstrapping to estimate the correct standard errors and to control for this first step of the estimation. I will show it also to you, not with a lot of rounds because of the time and of the computer, but I will just give you an example that it's better to do this to be sure that your the variance or the standard errors of your average treatment effect controls for the variance related to the propensity score or to the imputed common support and the normal sampling variation. Okay. This here, I'm just in this slide trying to tell you or to show you the advantage of the PSM and to compare it with a social experiment where I will have a group of individuals and I will, yes, Rashid.
Yes, thank you. I'm more to ask you about the minimum number of participants for PSM. If we
As any regression, the more the observations, the better your results. So you need to have a survey like nationally representative, but of course also depends on the number of participants. For instance, if I will take the example of Egypt, when I am talking about takaful program, not everyone in Egypt is getting benefit of. I don't remember the percentage exact, but it's not everyone is benefiting from it. So if I use the household survey of expenditure and consumption that is representative for the national representation of Egypt, it has around, I don't know, thousands households. And I have the question if they are benefiting from takaful or not. I can do this, but in the same survey, for instance, you have if the household is benefiting from the food subsidy system, the ration card system. This ration card, around 80% of the Egyptian population has it and getting benefit of it. So here it has no point that I can use PSM for the ration card system because almost everyone in Egypt is getting benefit of it. So I will not really measure its impact. So the more observations you have as any regression, the better results you have. But also your program or your treatment or your training should not be benefiting everyone. Otherwise, what is the point of doing this? And at the same time, should not be a very small number of observations who are benefiting from it. So, you have to make this balance. Tahani?
thank you.
Mrs. Sorry for asking so many questions.
No.
Actually, I want to ask about the means of bootstrapping and its relation with the standard errors.
Okay, so
When
yes.
we should use bootstrapping.
So to briefly answer this question, like bootstrapping is like a technique in econometrics we use. The simple idea as if you are running your model with your sample several times, but by several times I mean like 100 times or so. You need to have like strong computer and leave it for a while. It depends on how your computer is strongest. So the idea is that you are estimating your model several times. And so you have an estimated value of your parameter, different like 100 estimates, and then it will give you like the average of this one with the smallest variance. Why we are doing this? Because usually when you estimate a parameter and you want it to be efficient, you want it to have its variance as small as possible, no? Because this to be efficient, I don't want to have the variance of my estimated parameter very large. So this means that I am not really sure about. My interval confidence will be very big, and my estimates is not efficient. Usually when you estimate a model or a parameter given your model, your sample, you have already variation, normal sampling variation. And you can expect that your variance is large if you don't if I will take the OLS method, if you don't have all the hypotheses verified, you may have large variance, and this may affect the efficiency of your estimation. Here as if we are estimating on it's not as if it's reality. We are estimating the first step, the PI, the PX, which has already a variance because this is an estimated coefficient based on a given sample with a sample variation. Then you use this estimation to estimate again the treatment. So your variance will be very large because you are controlling for two variations, the variation from the sampling and the variation from the first stage of estimation. So when your variance is very large, this means that your coefficient is not as efficient, or your estimation is not efficient. So the bootstrapping allows you to estimate the same model 100 times, for instance, the same regression will give you a parameter with corrected standard error, a standard error that control for this large variation because they run the model several times and they give you the average of this. So it's like very simplification of the bootstrapping. And you will see, I will show you when you specify it, you specify the number of times the model will be estimated. Of course, if your computer is robust, this should not take long time and will give you efficient result with corrected standard errors for these different variants that exist in the sampling and in the first stage.
Thank you.
So just a simple idea, if you remember when I show you these tables that I draw, the values of the PX, the propensity score we calculated, give you the probability that an individual will be selected to be treated or to be participating in the program. But in in social experiment or in randomization, this propensity score is constant. The idea of the randomization is that everyone has equal probability of being selected to participate in this program or to participate in the training. Okay, this is an experiment. But when we have a survey that is not randomized and is not social experiment, we don't have equal probability for everyone to be selected to the program. What we are trying to do with the PSM, that we are trying to give equal probability to our calculate the probability for everyone to be selected based on the observable characteristics and to match between them. If you remember in my table, I have individual 1 who is, so here is the ID, here's the treatment, and here's the p-value. If you remember, the first individual was treated and his p-value was 0.7. And then the sixth individual was not treated and his probability was 0.75. In real life or in social experiments, this p is supposed to be 1 for everyone. Everyone or not 1 is constant in general, that everyone has equal probability of being selected. But in what we are doing with the PSM, I want to see individual 1 giving his characteristics. What is the probability of being selected to participate in this program is 0.7. For individual 6, given his characteristics, what is the probability of being selected to be treated in this program is 0.75. But so they are close. 1 is 70% and 1 is 70%. But in fact, 1 had been treated and had been selected to the program, and the other 1 was not selected into the program. So in real life, everyone, or in social experiments, everyone has equal probability of being selected, but not everyone is selected because of the randomization. For the PSM, I know that they didn't have equal probability of being selected. So I will calculate the probability of each one to participate and to be selected in the program using the observable characteristics. Then I will see who had been selected and who had not been selected, and I will match between them. Just to show you how here we are trying to mimicking the results or the randomization or the social experiments. As we said in the beginning, this participation can be affected by unobservable characteristics. This can raise concerns that still we have some selection bias in PSM methods that need to be. Okay. Let me stop here to break for 15 minutes, and when we'll return, I will start STATA, and with STATA, I will talk about the propensity score weighting. But just to break here, I think it's too much information for now. Any question, any comment before the break?
No, thank you. All clear.
So now it's 18:38 in Cairo time. So let's be back by 18, let's say 48. Let's take 10 minutes and be back, okay? So see you in 10 minutes.
Okay.
Hello, Racha.
Okay, so now let's start the fun, interesting part, STATA. And I'm sure a lot of things will be clearer when you see the data. Can you see my screen?
Yes.
Yes.
So I believe you have access to the do file and the data. So as I said, this data is extracted from the ELMPS 2006 for the sake of this training. just continuing what Chahir was saying yesterday, it's really important to have your do file with all your comments and for several reasons. It can be required by journal where you are publishing your paper, as he mentioned yesterday. You can be working with your co-authors, so it had to be clear. And even for you, even if you will not work on this paper for years, but trust me, from one week to another week, you may ask yourself, why I did this, why should why I use this command, what I had in mind. So it's very good to write comments and to be sure that you are clarifying for yourself when you read the do file or anyone else what is why you are doing this command. So this do file was based on a do file prepared by Ragi Asad and Caroline Kraft, who used to give this training before. So I'm working on the same do file with some modifications. In the beginning, just simple commands to clear. This your first, you didn't take stata with Chahir yesterday, no? The first stata session for this training for you, right?
Yes.
Okay. So this is just to clear if you have any other open files in your stata. Then I ask to set the more command off to have all the result once. Here, I'm just simplifying my life. If I'm working with a co-author or if I will be working on other computer, and I am someone who prefer to save several versions of the data set I am using. So I prefer in the beginning to set for stata where my original data is. So here I'm just writing the path of the original file or the original data. And I'm specifying another file that I call it temp directory or temporary directory, where I will save all my work. Why I'm doing this, instead of each time when I am opening a file or saving a file, instead of writing the whole path, and as I said, if I'm using another computer or I'm sharing this do file with my co-authors, they will have to change the path of each file in all the do files. So just for simplification, I start by specifying the paths I want to get the data from and save the data on it. And each time I am using a file or saving a file, I will simply write the $sign and the name of the directory where I am saving the file. So it's like a way to tell stata that I am calling. When I say I call original data, you have to go to this path that I am specifying in the beginning and get the data. And if I write temp directory, you have to go to this path and save the file I want to save in this directory, just for simplification. I don't know if you are aware of this command or not, but anyway, I will go through all the comments. The capture log clause, I want to allow stata to continue even if there are errors, to continue if there is a log file open or something, because the log file, so the do file, you have only the command. The window of the results, you have only the results. Once you close you exit your stata file, it will exit everything. The log file allows you to have the results and the commands and the results. So it is good to, when you wanted to share it with your co-author or with your supervisor if you are doing your PhD, or if you wanted to have both the results and the do file. I mean, it's important to store your output. So here I will open a new log file. I will save it with the date of today. Okay, and I'm asking to replace in case there was another log file open with the same name, which is not the case. You see here, it told me that there is a log file that is already open. So I will have to close. So here, when I run it from the beginning, it closed the open log file and start new log file with the date of today. Okay, we will use a data set extraction from the 2000 ELMS data, where we have 140 individuals or observations. and it includes a subset of variables from the ELMPS original ones and some created variables for the sake of this training. I save it, and again, because as I told you, I prefer to always save the data, especially that it's not that easy to get a data set. Once you get it, I highly recommend that you save it under name. You keep your original data somewhere safe, and you start working on the other new file, because you don't want to manipulate the data or drop any variable or any observations, and then you don't know how to get again the original data. So this is why I open the original data and I save it under a new name, which is the one I sent was shared with you. So just to be sure that whatever I am doing with my data set, I know that I am not manipulating the original one. The original one is saved somewhere else. Okay. As mentioned yesterday also by Chahir, it's really important to do the descriptive statistics. My supervisor used to tell me, go to play with the data. I consider the descriptive statistics is kind of playing with the data, trying to understand what is your data, what are the variables you have, especially if you are not familiar with this data set or it is the first time to work on it. It's really important to use it. So here, I simply start by, if there's any comments that you are not used on it or you want more clarification, please don't hesitate to stop me. So I just start by a descriptive of all the variables that exist in my data set. So you can see that we have the Egyptian governorates, the regions, if it's urban or rural, qism or markaz, which is one of the administrative decomposition of Egypt, lower than governorates. You have the individual code. You have a dummy variable for the marital status, if the person is married or not, of your education level, of the education level of the individual, if it's preparatory, secondary, above intermediate educational attainment, the age by the end of 2005. This is our variable of interest, current migrant, if they have a current migrant in, or this person is listed as a current migrant. Remit is listed a remitter if they are receiving remittance from someone else. You have other variables created like the age squared to see the nonlinear effect of age. If we have elderly person in the household, number of children less than 5 and less than 14. We have, this we'll use it later on, is instrumental variable migrant based on 2006. So we include an instrumental variable, the percentage of migrant as at Shaykha level. Shaykha assumes kind of neighborhood. So this variable will be used as IV. And we have several variables that we will use as an outcome, which related to the labor outcome status of women. So we have the first one is if she is participating in the labor force or not, female labor force participation for women between 18 and 49, the standard definition that they are doing a market work. We have the wage and salary work of women, we have non-wage work, and we have participation in subsistence work. So these are our 4 variables of outcome. I will focus more on the first one, but you can do the same exercise for any of this. These are other variables that we created. Other variables that we use, I don't know if you are familiar with gender literature or female labor force participation, but in a lot of cases, the characteristics of women and their households are not the only explanatory variables for her labor force participation or of her empowerment. Women, they are affected by the society where they live. So this is why usually it's important when you are tackling women empowerment or female labor force participation to include variables that reflect the community where they live. Like in Egypt, it will be, for instance, characteristics of the governorates where she lives. So here we have some variables at not the governorate, the Shaykha level, which is better because it's like bigger level, higher level than in households, but still less level than governorates. And it was found in the literature that in a lot of cases, women's status is affected by the society where she lives, like by traditions and norms. So here we include 5 variables reflecting the sheikha or the community where she lives. Share of males with intermediate degree, share of males with university degree, share of men employed in private sector, share of men employed in agricultural sector, and share of men unemployed. This can reflect the society where she lives. And other variables, we'll see if when we'll use it. For the regions, we have 5, we decompose the Egyptian governorate into 6 regions. You have Great Cairo, Alexandria, and Suez Canal. Usually we have both as metropolitan governorates. Then you have urban areas and rural areas divided into urban Lower Egypt, urban Upper Egypt, rural Lower Egypt, and rural Upper Egypt. Okay. For urban, we have urban and rural. If this variable equal 1 for urban, 0 for rurals. We have the marital status. All these are variables that we use to include in our analysis, our X variable. We have 53% or 54% of the sample who is not married, single, and you have 46% who are ever married. Ever married means married or widowed or divorced. The variable that we'll use it as treatment is the current migrant. So we have 4.5% of the individuals reply that they considered as current migrant or have current migrant in their household. In fact, also the literature shows that sometimes when female labor force participation increase in household when they have migrants, because sometimes as the father or the husband is not here and is migrant, and she will be the one working in Egypt, or he will be sending her remittance. She can use it for creating a new project or something. So in the literature, migration status of the household or of the husband or the father can affect the female labor force participation. This is why we are including. So here, if we have listed as migrant, and here, if they are receiving remittance, and we have 3.27% of the sample who are receiving remittance. For the age, we have here one of the advantage of the descriptive statistics that you can see if there are typos or data entry mistakes in the data set. So here in the age, you see that we have -1, which is no one is having -1 years old, and you have the maximum 95. So usually, if you will work with the whole data set, sorry, you will have to correct for this. But any case, I will focus on a specific age group between 15 and 49, the age of where we assume that women would participate in the labor market. So I will in any way remove or drop all the observations that women have not, or individuals have no this specific age. So I will keep the age here. This is why, again, I am asking you to always have a safe version of the data placed in safe place, not you are going to affect. So here I drop the wrong observation or the observations I don't need. So now I have all observations aged between 15 and 49. And I will save it under new name. These are the variables of interest I showed you. Okay, and these are just to show you the share of male. So here I am trying to see the share of male with university degree by sheikha. So just to show you that we can use this command where it will give us the mean and the minimum maximum standard deviation of each variable by sheikha for all the sheikha that we have. Okay, any question, any comment on this commands? Any question, anything is not clear? Okay, I will take also silence as yes. I see that you don't have any question. Okay, so our treatment is migration, and we'll check also if we have time for remittance on labor force participation. So my treatment or my analysis having migrant in the household or current migrant in the household, 0 otherwise, and our outcome variable is labor force participation for women between 20 and 49. Okay, We created variable named age group. It's already created in the sample, which is dummy variable equal 1 if the individual is a woman in the specified age, 0 otherwise, in order to focus on this sample, okay? And as I defined in the beginning, using the global command, the path of the place of my files, I will also specify to Stata using also global command, what are the variables that I want to include in my analysis? Or in other words, what are the observable characteristics I will include that would affect the migration status, which is my treatment variable, and the labor force participation, which is my variable of interest or the outcome of interest. What are the variables we are including here that according to the literature and the theory, and we know that it affects migration and affects female labor force participation? We have age squared for the nonlinearity of the age effect, the education level, the ever married dummy if she is married, widowed, divorced, or single, number of children under 6 years old, and those aged between 6 and 14 household. You know that sometimes if the number of if we have children, if women have children less than 6-year-old and not going to school, they would not maybe work. So it's always important to include the number of children in the analysis, and also it can affect migration because men may decide to migrate to provide their households who has children with enough income resources. We have the number of elderly also in the household. And we have the average monthly non-labor income from other sources than labor. And as I mentioned in the beginning, we will include community level variables, the share of males with intermediate university education, those who are working in private sector, who are unemployed, and who are working in agricultural sector. So these are our variable axis, observable characteristics that we know that it can affect our treatment and our outcome variable. I will put them in the vector of x1 and ask Stata to, whenever I am calling you this variable, this vector, you will bring me these variables. So I will run it, okay. And here I wanted to see okay, there is no point to do the sum here because we have a couple of variables that are not, I mean, this variable ever married is dummy variable, but it gives me the average. So I will sum the vector of x's for women who are between 20 and 49, who have remittance income, okay, even if there's no migrants, they are receiving remittance from abroad. So here we have 7791 observation. We have all the average of all the variables. Here also for the community variables, just to get an idea about the variables we will include given this sample. Okay, now, as I mentioned that Stata, the PSM can be done all the steps we talked about, the estimation of the probit or logic model, the matching, the comparison between the average values of the X variables between the participant and non-participants, all this is done by only one command, but we need to understand the different steps to be able to analyze it. So the command in Stata, I don't know if you have it or not, because I'm using Stata 11, so maybe that's why I had to download it. But if you have the new versions, you may have it, and if not, you can simply download. So the command is psmatch2. So you can just write find it psmatch or help psmatch2, and it will give you the link where you can download. All right. So usually you will have it if you have updated dataset, sorry, Stata version. Okay, what is in our case is doing, so remember, as I mentioned, our y variable, if I return to, where is the, if I return to my example, to my, to the slides, our y is here in this case, is the labor force participation. Is one of the outcomes we are interested in. I showed you 4 variables, but now I will focus on female labor force participation, if she's participating in the labor market or not. And the T, if she has a migrant in the household or not, and see if she has a migrant in the household, see if she has no migrant in the household. This is our treatment. So what we wanted to do, according to our example, first I wanted to, as we, if I return to the steps here, we wanted to estimate the probability of participation using a probit or logit model. What is the participation in this case? It is the fact that you have a migrant in the family. So this is the first thing we will do. We'll estimate the likelihood of being migrant. And what is our variable of interest is CMIG. This is our treatment variable, migrant for the sample of women who are between 20 and 49 years old, and we will focus on rural areas. I will not include urban areas. Of course, I mean, I can include both and add a dummy variable for geographical location, but here we prefer to focus on women living in rural areas and who are receiving remittance. So my sample is women living in rural areas receiving remittance, whatever the migration status of them is, of their husband is, and they have between 20 and 49 years old. Okay, I will estimate the likelihood of being migrant for this sample, and the propensity scores that are calculated for our outcome variables for the probability of being migrant, I will use it to match for the different outcome variables. As I said, we can calculate it for female labor force participation, for wage and salary, for non-wage work, and for participation. Here it will be, of course, from 20 to 49. Then, so first step, I will estimate the probit or logit model. I will use the p-values calculated to match between participants, women who have migrants, and non-participant, women who have no migrant. Okay. To be sure that my matching is correct, I will test the difference in outcome between the match and sample. But before doing this, I wanted to compare between the average value of each variable X of the treated and the average value of each variable X of the non-treated, to be sure that my comparison is or my matching is correct. As we said, if there is any significant difference between the two sets, this means that we are not doing a good job in matching. We will, we can use kernel function, and we can use other options of kernel functions, and I will show you if we'll use the closest n observations, which number of n we will use, or if we will use the other methods like the closest observation, not the closest n observation. Okay, so now so this command psmatch2 is supposing to do all the steps we want to do. Estimate the likelihood of being migrant to calculate the probability for participants and non-participants. We will have a match between the participants and non-participants based on the value of px. Then we will compare the outcome. We have 4 outcomes, but we can start by 1 outcome, or we can do the 4 just for simplification. And then we will compare, after doing the match, compare the outcome between the participant and the non-participant. Okay? So now let me get this here. So here's a command is psmatch2. Okay? You write the variable, your treatment variable, which in our case is current migrant. So this is a variable I want to calculate the likelihood of it, to calculate the px and then do the matching. I include all the regressors or x's I wanted to include. For the sample of interest, of course, if I want to do it for the whole sample, I will remove this part. But I wanted to focus on the age between 20 and 49, those who are not receiving remittance and who are living in rural areas. Then, so you have your treatment, your variable x's, any condition if you want to condition your sample, and outcome. So you have comma outcome, and here you write the variable of outcome of interest. In the example of takaful, current migrant will be takaful if she is participant of takaful or not. And the outcome will be the indicator of women empowerment, or her income, or her children education. Here is a women labor force participation, and Here I will start with the kernel, which is the most complicated or more complex way of matching based on the weighted average of the whole sample or the whole group of the non-participant, and we'll see what it will give us. Okay, so
Excuse me, Racha.
yes, Hassan.
Please, you may have mentioned this before, but the original data, where can we find it?
On the ARF website.
Okay, so we can download it on the air. Okay,
Yes,
thank you.
on the ARF website, you have the whole panel data set. So we have 98, 2006, 2012, 2018 for Egypt. Have for Tunisia 2 rounds, for Jordan I think also 2 rounds. You have really very rich set of data, different data sets from different countries of the region. There is a formulary you have to complete what you are doing, what you are going to use the data for, and usually you have an answer quickly.
The one you're using here is the one for Egypt, right?
Yes, it's the one for Egypt for the year 2006.
Okay, thank you.
Please, Racha,
yes,
can you share with us the data that you work on? And we apply with you.
I sent it. I don't know if ERF team sent it to you or not, but I don't know if I can share it using the chat. Let me see. Just a second. Yes, Nami shared it with you on in the chat. You have a link. Did you see it in the chat?
It's only for the do file without the data.
Yes, it's only for the do file, not for the data.
Let me see if I send it correctly to Namis. Sorry, I shared the wrong file with the ERF. I will send the data. Just a second. Okay. I share the data. Sorry for this. Okay, let me get back to something. So here, this is, as I said, one line of PS match command, which is a command used for the PSM, and you have these results. What are these results? And here I'm specifying in the data set, in the do file, you have the logit regression, as you can see here, or here, in fact, it's probit regression. You have the average treatment for treated, our variable of interest. I will talk about it. And you have how many of the treated and untreated are on the common support. If I return back to here, you have this blue area. We have how many persons are on this common support of the PX values that take between 0 and 1. Let's go to this results. So here you have the probit regression of your estimation of the likelihood of being treated or to participate in the program, and in our example is to have a migrant. Okay, and you have all the variables, so you can here check it as any regression. You can see what are the significant variables. We can see that the elderly in the household number of elderly, of the share of elderly in the total household size is significant and can increase the likelihood of being migrant. Okay, the share of male in working in private sector, the share of male in agricultural, and the share of male unemployed also affect the migration status. Okay, the data is shared on the chat. Thank you, Namis. Thank you so much. Okay, so here, like any regression, you have all the variables you include in your model. Of course, you can see if there are variables that are not significant, you can decide to remove it or to include other variables. Here we can see, I mean, if the theory and the literature say that we should have it, we should have it. But sometimes there are some variables you are not sure if they are really affecting the participation or not. Here you should consider it. But you can see that it's not age or education that would affect the migration status, and mainly the number of elderly, and also, sorry, I forgot this, the number of children under 5 years old. This means that when the dependence ratio in the household increase, the number of children less than 5 and the number of elderly individuals will prefer to migrate to get more income. And of course, the community where they live also can affect their migration decision. Okay, so this, based on this one, is supposed to create the P-score. Let me return one step back. So I will clear this. I want to show you something, so I will just repeat what I was doing before the step. Can you see here the window of the variables? You see the last variable we have is the agricultural land, total agricultural land owned by the individual, by the household, okay? When I will run the PS match command, I want you to try to look at these variables to see what would happen. Okay. If I go back here, you see that there are several variables, new variables that have been created. The first one is the P-score. This one is the propensity score. Let me show you what I was drawing in my presentation. Of course, for some individuals, there was no. Okay. So here, this is what I was, if you remember, I was trying to draw it to you in green in my presentation. You have here the individual ID, and you have here the P-score of being migrant, of having current migrant, okay? You see that the values of the P-score varied, 0.003, you know, it's continuous, it's not, this is why we said that we need to see the closest observation. We need to find a way to define what do we mean by closest observation. If I will add the treatment variable, okay, you see, so all this individual, first to individual, the probability, the likelihood of having current migrant is 0.003, according or given the characteristics we include in our model. In fact, this person has no migrant. So here there is a match between the score given to these individuals, given their characteristics, and the reality. I'm trying to see if there's any one observation. Here, for instance, look at these two individuals. The one in line 784, the probability, the likelihood of being migrant of being treated given their characteristics is 0.042222. And in fact, in reality, they are treated. Their current migrant status is 1. While the individual in the line 785, the probability, the likelihood of being migrant, of being treated, given their variable axis is the same, is almost the same, no? Is 0.04222. And the current migrant status is 0. So these two persons can be matched, no? Because according to their characteristics X, their Px value, their likelihood of being selected is almost equal, but one is treated and the other one is not treated. So what I can do is to compare the outcome between this individual and this individual. Okay, are you following?
Yes.
I'm trying to return back to the example I gave you. Okay, yes, these two individuals. So you see, these two individuals, they have almost equal score regarding the likelihood of being treated. One is treated and the other one is not. And we can compare their outcome variables, which is the labor force participation. But here, both individuals are participating in labor force. So here we don't have a difference in their outcome. Okay? Here, two individuals, but here they're not treated. Here, for instance, they have also almost equal Px. One is not treated and one is treated, and both are not working. So we will do this match between all individuals. We can do this match. Of course, we are not doing this match. SATA is doing this match using the closest neighborhood, as I am doing the closest match, or the average of the n neighborhood or neighbors observations, or using kernel function, and they will compare the outcome of this group with the outcome of this group. So just this to show you how the p-value is calculated. The p-value is the estimated likelihood based on the probability estimation we have, but Stata do it by itself. We don't have to do it step by step. So Stata calculates the likelihood of being, estimates the probability model, calculates the p-score, did the match, and this is the line we are interested in. So here is giving you the average treatment effect of the treated. So for the treated, their outcome, the estimated coefficient of their outcome is 0.4, okay, which is this equation. This is this average treatment effect of the treated. So Stata did the likelihood p-values, did the match, but here we are using the kernel function. They calculate the kernel function for the output of all the non-participants of the control group and make the difference and calculate the average and give us the results. So for the treated is 0.4, for the controls is 0.31. Here is the difference. So the difference here is positive, which means that the outcome for the treated are larger than the outcome of the non-treated. Again, this value, this difference is the variable or the indicator we wanted to calculate, which is the average treatment effect. Is the difference between the sum of the difference between the treated and the control group, the closest one using kernel function, divided by the total number of treated, and it gives me this value. So this value is positive, which means that the treated, the outcome of the treated, those who are benefiting from the program, or in this case have migrants, is bigger than the value of the outcome of those who are controlled. Okay, so this is the difference. Is it significant or not? We have simply to compare the t-statistic and with the two, or to check the standard error, so we can see that there is significant positive effect. What can we conclude from this? That female labor force participation among households who are treated, who have migrants, is larger compared to the outcome, which is the labor force participation among non-participants, which means that we can conclude that the treatment, which in this case migration, have positive significant effect on the non-migrant. So on the household, sorry, on the outcome variable, which is the female labor force participation. Again, so this table, what Stata, how it calculated, Stata calculates the probit, estimates the likelihood of being migrant, of being treated, did the match using kernel function as I asked, and compare between the outcome of the treated and the outcome of the closest match in the control group, and give me the difference. The average treatment effect is 0.086. It's positive, which means that the treated have higher value in their outcome compared to the control. And according to the t-statistics, it is significant positive. At this stage, you should be surprised and impressed by the fact that Stata did all the job for you, all what we have been talking in the last 2 hours. And according to this, we can conclude that migration increased female labor force participation in Egypt in 2006. And here it shows you the common support between, I mean, we have 344 observations, 237 treated, and they are on common support between the density of the p-score of the treated and density of the p-score of the control. We can have it graphically. I will show it to you. Okay. Yes. Graph. Is it clear? So here, yes, you have the treated and the untreated, and you have for each value from 0 to the 1, but here we have very low values. You can see how many observations untreated and treated have common values. So here, all these red ones and blue ones have common values, and these are the one matched together. So this is supposed to look like the figure here, where the graph. But you have to imagine it because on the other side. Is it clear? Do you have any question, remark?
Says
Yes.
always me.
Pleasure.
What does mean common value, or what does reflect when we find a common value between treated and untreated persons or observation or participant?
Okay. Common values mean that all the persons who are, let's take here this this part one, this column, okay? All the persons who are in red, who are treated, and all the persons who are in blue, who are untreated, have same values of the likelihood of being treated. Their px value is common. So we can match people from here with people from here. And this is the aim. In fact, if you remember, let me return here. Here is the p-scores. I need to find individuals who are treated and untreated, who have common values, to be able to match them together. Because as we mentioned, in social experiment, when it is randomized, everyone has equal probability of being selected. But some are selected randomly and some are not. Here we don't have the same situation. So what we are doing, we are trying to giving a likelihood of selection to individuals given their characteristics. And then we will take individuals who have common value, who have equal values of being selected, and then see who had been selected or not. Okay, if Aya and me, both we have the same value of p-score, so we are on the same common support, we can be matched together if she is not selected and I am selected. And then you can compare between our outcomes. But if I don't have anyone who has common value as my p-value, you cannot match me with anyone. So this is why we were saying that you need to have enough large common support to be able to match individuals together.
If I understand, here we try to explain the hazard with science, no?
In fact, in the opposite, we don't have a hazard, we don't have a randomization. So we are trying to explain, we try to mimicking the fact that as if we are in random situation, as if we are all having the same likelihood of being selected, but some are selected and some are not selected.
Okay.
So we are replicating the hazard. In hazard or in random situation, we will all have the same probability of being selected, but randomly some will be selected and other not. Here we know that it's not the case, that people are selected to be treated in the program based on some characteristics that can affect this selection and affect their outcomes. This is creating bias selection. In order to overcome this, we are mimicking the situation by giving individuals equal scores given their characteristics and taking, let me repeat this command again. So for each values of P, I will match everyone in the treated with everyone untreated and compare between their outcomes. Because simply, I mean, let's take, if you compare, are you done with your PhD, Tanya, or not?
No.
Okay, this is a good example. If I compare my salary with your salary and my salary is higher, we cannot say that the only difference is that I have a PhD and you are not. We cannot conclude this simply because we are not, maybe we don't have other common characteristics. Maybe in addition of having PhD, I am older than you, I am from a different country, I have different education background. So all this difference can explain the difference in salary between you and me. But if both of us have same age, we are living in the same country, we have the same education level, we have, sorry, not the education level, we have the same background in education, and the only difference between you and me is that I have a PhD, we can conclude that I have a higher salary because of my PhD. But as long as we don't have the same characteristics, we don't have the same score, I cannot argue or conclude that the PhD is the result why I am having higher income. It's the same thing here. I cannot compare, I just can compare these individuals in this part with these individuals in this blue part because they are both have equal probability, which means they have equal likelihood of being treated or selected. But only the red were selected and the blue were not selected. So any difference between both now, between those and those one, we can say that yes, this is because of the treatment or the group. But for instance, you cannot compare this. Can you see my arrow when it's moving? Yes, you can see it, right?
Yes.
You cannot compare these persons in blue with these persons in red here. Why? Because these persons in blue had a probability less than 0.1 to be selected in the treatment and they have not been treated, while the persons in red here had a probability of being selected of more than 0.2, which means that in general, the characteristics of this group in red here were more likely to be selected in the program more than these blue ones. So you cannot compare between them. You cannot compare the outcome of these red ones with these blue ones because these red ones have different characteristics that make them more likely to have migrants and more likely to have women participating in labor market. So you need to compare persons who are equal. And how can be equal? By having similar common support, which means similar propensity score values.
Great, thank you.
Okay, let's do other, make the same exercise, but with other, how to say it, matching method, okay? Of course, you will find, I mean, you have the do file, you can try all the exercise, different exercise, but here just for sake of time, I will select some matching methods to do. So here I will use the one-to-one match here. And I will try it once without any caliper, without any limit. And I will try another one with limit, okay? So here, I am doing the one-to-one match, okay? By adding the option ties. So if you remember here, I had, when I wanted to use kernel, I use the option kernel. Here I use the option ties, which means one-to-one matching. This is the default one. And I will try it once without any limit. So I will ask Stata to choose the closest one, even if the closest one has a difference of 0.2 or 0.3 as difference between the p-values. But on another time, I will ask Stat, no, I want to caliper. I want to maximum the difference between the both values of p is 0.01. And let's see what the result. So it's the same. the same command with the same variables, everything. But for robustness check, as we said, that the matching method can make huge difference in the results if there's something wrong in your analysis. So I will just change the matching method. And let's see. Okay, so they are estimating the SATA is estimating the same probit model. I mean, the results of the probit model should not change because it's the same model anyway. It's the matching method that would change. And here we can find that we have a positive difference. However, it's not significant. So here we find that there is a difference with the kernel methods. That still we have a positive effect, but when we use the one-to-one matching, it's not significant effect. Okay, so now we have one method telling me that you have positive significant effect, and another method telling me that you have non-significant positive effect. Let's try a third one. I will use the same matching method ties one-to-one, but I prefer to make caliper because, as I told you, the one-to-one match can match me a value of P with 0.02 and with 0.1. So here there is 0.08 points difference. So I prefer to have it more close values. So I will do the same thing. Same thing. Here we have positive effect, but not significant. Okay? So the two one-to-one matching is showing me that we have positive effect, but not significant. And the kernel method is showing me that we have significant positive effect. Let's try another method, the one-to-one match. Sorry, not one-to-one. The n closest neighbor. So here I will use the n5. So I want to compare the outcome of each treated individual with the average of outcome of the 5 closest observations. Okay. And I will also put a caliper option for the closest one. Okay, so here, same PS match, current migrant, variable X, same observations, outcome. Let me focus only on the labor force participation. And I'm specifying N5. This means that I am telling SATA to do the match using the closest 5 N observations. Let's see what it will give us. Same probit. And here you have positive difference, but is significant. So here with the kernel and the 5 neighbor areas, neighbor observations, we have positive significant effect. And with the one-to-one, we have positive but not significant. I would conclude here that we have positive significant effect simply because it's more, I mean, the closest observation is the simplest one. Is positive but is not significant, but in 2 other methods we have significant positive effect. We can try with, for instance, instead of 5 we can do 3 and see what will give us. It's also significant. So you see, you have to try. I mean, in other cases you can have the same all giving you the same results. I mean, it always should be positive or negative, but the idea is significant or not significant. And here, as I said, you have to do several methods to be sure that your results are robust. One other thing that we didn't do it. You remember I told you that you have to compare to be sure that your matching is correct and there is no difference on average between the variables X of the participants and the variable X of the non-participant. So to do t-test to compare between the average values of the 2 sets of variables. We use the command ps-test. So ps-test create to you this table with all variables, the mean in the treated and the in control, and if there is bias or not. If you don't have any significant difference, you see here all the difference are not significant. This means that you are doing a good job, that there is no significant difference between the average values of the variable X's of the treated and the average values of the variable X's in the control. If there is no significant effect, this is what you wanted to do. You want to be sure that these two groups of individuals of observations are having similar characteristics. If you don't observe this, or there is one variable where there is significant difference, this means that there is something wrong. So here, this means that we are doing good job, and we can conclude that we have having migrant would positively increase the number of, the female labor force participation. Okay, here you have the exercise of bootstrapping. Let me quickly, in the last 10 minutes, I wanted to return to the weighting sampling, and you have the exercise in Stata, but just to get the idea behind. Yes. So one way to use the PSM, because as you noticed, when we estimated the probit model and Stata created the p-score, so p-score is the probability of being selected into the program given your characteristics, okay? So one way, instead of using the PSM, I can estimate the probit model, get the p-score, and use the propensity scores as a weight for the observation, like a sample weight. So instead of giving the propensity score, doing the matching, and then compare the outcome here with the outcome of the non-participant, what I will do, I will estimate the likelihood of being selected, which is the propensity score, and then using as a weight. Specifically, we will use what we call inverse probability of treatment weighting. What is this idea? The idea is that, especially if we have nonlinear modeling, we will give higher weight to the individuals who were supposed to be selected but had not been selected, and the opposite, a lower weight to the individuals who were supposed to be selected but had been selected. Let me show you the equation. So the first step, I will create the PX, the propensity scores, using the variables we are including. The first step, as we did till now, I will calculate the p-values. Then I will create the weight. What is the weight equal to? It equals TI if the person is treated, divided by the estimated value of its propensity score, plus 1 minus TI divided by 1 minus P hat I. Let me show you. So if the individual is treated, TI equal 1, so we have 1 over PI hat, which is the estimated propensity score, and this one will be eliminated, okay? If the PI score is low, this means that WI will be low or high value. Again, if the p-score is low value, which means that the probability that this individual should be selected in the program given their characteristics is low. In this case, the weight will be low or will be high?
Will be high.
Will be high. So if P hat I is low, which means that the individual is less likely to be selected in the program given their characteristics, we will give them high weight. And the opposite, if PI is low, which means that, is high, which means that the individual was highly likely to be selected in the program given their characteristics. I will give them high weight or low weight? High weight or low weight if the p-value is
Low
high?
weight.
Low weight. So here, I will say, okay, I will estimate an OLS regression, but I will use weights using the propensity score, so I can give low weight for the individuals who were treated and their likelihood to be treated was high. While the individuals who had low likelihood of being selected, but they had been selected, I will give them high weight. Same thing for the not treated. For the non-treated, the WI will be 1 over 1 minus PI hat. If PI hat is low, the numerator is high, and all this will be low. So for the non-treated, if the individuals had high value of being treated, but they had not been treated, they will get high value of weight. If they were not treated and they had low value of being treated, I will give them low weight. So the idea is that if you had low probability of being selected and you have been selected, or low probability of not being selected and you have not been selected, I will give you low weight in the regression. But the opposite, if you were not supposed to be selected, but you had been selected, or you were not supposed, or you were supposed to be selected, but you had not been selected, I will give you high weight. And if I return to stata, so here what we are doing, so I do the first step, okay? I ask stata to calculate P score for, doing the probit regression. And I want to save the value of the P score in a variable called score underscore 2. You can do also a probit or logic regression normal one without the PS match. Okay. I don't know why there is something here wrong. Okay. Yes, here just is giving you the same idea of the graph I showed you, but it's giving me the values of there are 412 persons who are not treated who has this value of P, and only 8 who have been valued. So there is no equal balancing between those who are treated who are not treated, but we have here the common support. Okay, and then I will create the weight using the score. So this equation is exactly what I had been showing here. The weight equal, if the person is treated or not, divided by the estimated P score, plus 1 minus being treated or not, divided by 1 minus P score, to give high weights for those who were unlikely to receive treatment but did, and those who were likely to receive treatment but did not. Okay? I think he will not... yeah, I calculate weight. So if he come here, you will see the variable weight. And then I can estimate here. I will not estimate OLS. I will estimate probit model, because my variable of interest, my outcome of interest, is the probability of being participating of labor force, because our outcome variable is female labor force participation. So my my model will be probit, and my Y is the probability that the woman, that this woman is participating in labor market. Okay, I will include the migration variable, my treatment variable, as a dummy variable, and I already use this without weight. Here is the regression, the normal one that we said yesterday that it will not be efficient parameter because we have the selection problem. So here I am not correcting for the selection bias, because here I am not including the weight. I am just estimating the female labor force participation using treating the migrant as a dummy variable, here without any variable X, here with a variable X. So I can estimate it here just to show you the difference. And here I found that having a migrant positively, significantly affect the likelihood of being participant in the labor market. Okay, but I know that this probit, so this is right, with the PSM we found the same results. But this this probit regression do not correct for the selection bias, because here I am including the migrant variable as a dummy variable. I know that there is selection bias and I didn't use a PSM. I can use PSM, or I can re-estimate the same regression, as you can see here, the highlighted part, but I am using a weight, and this weight is created using the score of the PSM. So I will estimate this regression. Okay, here without any X's, I was just giving you the different examples. Let me give you X. And here I can see that having a migrant being treated have a positive significant effect on female labor force participation. It is significant, it is positive. But here with this regression, because I am using the weight of the propensity scores, I am sure that I am correcting for the selection bias. So here is another way to measure the effect of specific treatment or program on specific outcome, but instead of using the PSM, you can use the weight, the propensity scores, to calculate a weight and estimate an OLS or probit depending on your outcome variable using this weight that corrected for the selection bias. So this is another way of using the propensity score values. Is it clear? Any question? Anything not clear?
Is Rasha?
Yes, Rafi.
The test statistic should be above which value to be significant?
In general, the common rule is above 2. That is
2.
2. I mean, if I return back to the PSM here,
Okay.
here it should be above 2 to conclude that it's significant.
Okay. I try to run the program, but I cannot. The data give me the message about the file. It couldn't find the file.
You are running the
Type-
file as it is?
Yes.
Yes, it will not work for you because remember, here I am specifying the path of on my computer. So you should change this path.
Yes, I changed the two original data and the second line. I
And
should change just the first one line.
No, 2, because these 2 paths are on my computer, so you should change both. But you should, in the original data, you should specify the path of the file where you have your data.
Okay.
Because if
It worked for me. I think the problem is with the name of the file. So the name of the file as sent by the ERF is different than the name of the file here. So we just,
Yes.
and in the original data and international migration data, we change this as the name of the file that was sent to us by the ERF, and then it works.
Okay, yes. So yeah, I sent you the file with this, the file PSM data age 1549.
This the
So we need to
original?
put this name, yes.
No, this not. So this why it's not opening, because it's not the same name of the file. You have to change the name of the file. Or you open it and you work on it without doing all these steps, because all these steps depends on another name of the file.
Okay.
So that's just change it and see if it will work or not. If not, I mean, I don't know if you have my email, but I can send you my email on the chat, and you can send me anytime if you have any question, or I can send. I don't know. I don't know why I cannot send message. I can write you my email here, and if you have any question. Racha is more. Okay, so try to rerun it and see if it will work or not. But I think it's only problem of name of the file. And if you have any question for anything, you can send me. Or anyway, I will see you inshallah next Tuesday.
Just a,
Yes.
sorry, Rasha. Just a question. When will we be able to get the recordings?
This question that I don't have the answer. The ERF will be answering. The ERF team can answer this question, but I believe it will be at the end of the whole training. If I'm
Okay,
not
so we get in touch with Sophie or Chahir or
yes, after the end of the training, you will get.
Okay, great, thank you.
Aaron?
Yes.
Would it be possible to share the comments before the training next week?
Yes, sure.
Okay, thank you very much.
Before. Any other question?
Your email is Nabil.
This N Nabil is the email of our colleague from ERF, Namis Nabil. So if you have any question regarding the organization or anything, you can send to her. My email that I showed you, if you have any question regarding status, Hadoop files, or what I did today, or what I will do next Tuesday, inshallah, you can.
Great, but I didn't find your email address.
Okay, I will share it again. Can you see it?
Okay, just let me.
No, I think only the ERF can share with us the chat. They can
Yes.
write the chat log.
That's why I couldn't share it on the chat. But here you have it. If you have any question.
Great, Racha. Thank you.
Thank you. Any question, any comments, anything?
Sorry, I write the message, but how long can we watch the videos after the training?
After the training, they will be shared with you the videos, the recording.
Okay, thank you.
Okay, thank you all. Have a great night, great weekend, and see you next week.
Thank you.
Thank you, Racha.
Thank you.
Thank you.